In this presentation, we will be looking at one possible implementation of the derivational search function, which is the core of the executive layer in the whole computational infrastructure. And then I will run the script to show what it does concretely. Before I look at the implementation, let us just make a few overall comments about how this source code material is organized. So all the scripts that I will be talking here can be found from my GitHub page under a project, a templates project. I will show the address presently. And every script I will be discussing has a name that identifies it. And they can be simply downloaded from there. To run the scripts, you of course need Python installed in the local machine. Python is a program which reads these text files. So the scripts that I'm going to show are simple text files. And the Python is a program which is reading those lines and will transform them into instructions that the computer can understand. And so this means that if you take this text file, the source code, and you make changes to that file, they will immediately transform or translate into changes into the behavior of the program. So that allows simple experimentation. It's, in other words, simple to modify the scripts that I'm showing here and try different variations or do computational experiments. But let's begin by looking at the source code itself. I will put it up here. There it is. First of all, I mentioned the source code, some things about the source code. So this is the address for where you can find these scripts and many others. Some of these scripts will be covered in these presentations, but there are also others that are discussed in some of my research work. And then the script itself is template 2.2. And let's go to look at the derivational search function. It's here. And this implementation mirrors very closely the pseudocode presentation I provided in the first part. We have the name of the function, and as you can see, it takes the syntactic working memory as an input. Now, this is simply a set, or I don't remember, maybe it's a list, can't remember which one, of phrase structure representations. The first, when we call this function first, it will be provided simply a set of primitive constituents that correspond to the words. Now, as I mentioned already, this function presupposes that we have defined the notion of phrase structure. And this is defined in the same script here in the beginning. It's a class phrase structure, and I will be talking about this in a later presentation. Now we take it for granted. And as I already pointed out, the reason for this is that there is so much controversy around the notion of phrase structure, what type of structures they are. So it's better to put it aside here. And indeed, this whole function is written in a way that it can be applied or it can be used in connection with any type of grammatical theory or hypothesis. So the first thing here is that we simply check if the derivation is complete, and if it is complete, we go to process final output, and that's the post-syntactic function. I will look at that later. You can see that the functions are already here. They have their separate definitions. And if the derivation is not complete, then and only then, we go for the recursion. And here is the first loop, the outermost loop, where we go through all the syntactic operations, the assembly operations, and whatever else we might have in our theory. And as you can see, I have the syntactic operations here is a separate data structure which simply contains a list of these assembly operations. Now let's just look how I've composed it in this case for the purpose of this simple example. So the notion is defined here, and it is a list of, so this brackets here, the outermost brackets in Python create lists, and each item in the list, and here we have only one, is a tuple that contains 4 things. We have preconditions for the operation. These regulate the input triggering conditions, and they block the operation from happening from certain cases. Then we have the operation itself, and this is just, they are defined as separate functions in the phrase structure class. And a phrase structure class is where I define anything that has to do with phrase structures. So we can go to quickly to look at it here, what it means. Here it is standard merge. So we create a new phrase structure from two constituents. That's what we are doing there. Let's go back. This is the number of arguments this operation requires. In this case, it's 2. The operation creates binary branching constituents. And finally, its name here. And the name is provided in this list because later, or actually perhaps already here, I created a supervision layer where all the operations are logged. So the program, the script will write a text file which records everything it does, so that we can again supervise its function. We know that what it's doing makes sense and it's correct, and especially when it does something that is not correct, we need this information to find out where the problem is. So this is a tuple which contains these 4 elements, and they are always returned, as you can see here. When we take all of these items, we return all these 4 items here for each tuple and give them names. But as you can see, I have only one operation now here in this script to make everything simple. But if you have other assembly operations, they would be listed here, and they would need to. We had to provide all of this information for each of them. So let's move further. Here then, after we have selected one of these operations, we then take every possible tuple of phrase structures in the syntactic working memory, n tuple, depending on how many items the operation requires. The n here represents this. So for example here, if we look at the merge, which have 2 objects always, we are picking out all pairs from the phrase structure working memory. This picking up of these pairs, I'm using a Python function, existing function that is in the Python standard library. It comes from the iter tools module, and the function is permutations. And this does these permutations automatically if you don't want to code themselves, or if you don't need anything special, you just need all the pairs from the set from the syntactic working memory, then you can use this function. And they come now in the well-defined order, each of them. The SO here is are the pairs, syntactic objects. That's where this comes. So now we have this loop. We go through all the operations, and every operation we take all the possible inputs from what we have. And then I have an extra condition that we didn't have in pseudocode. I'm testing the preconditions here. So if the preconditions do not hold, then we don't do anything. We simply ignore that operation. This notation means that we are feeding these preconditions with the separate objects and not the pair itself, but we extract the items from the pair. Next, we create a new semantic working memory, new set, and that set will be all the elements in the old syntactic working memory minus those for which we applied the which we will apply the operation. So always when we apply an operation to the items in the syntactic working memory, we will remove the phrase structures that were inputs to that operation and replace them with what comes out from the operation, and that happens here. This represents conjunction. So we take this set plus this set. And this latter term here is the output of the operation. And then we call the derivational search function recursively by using the new syntactic working memory. And that's it. I'll make a couple of comments about this before we run the function and see what it does. One thing is that, as you can see, this function doesn't depend on the details of the grammar or the hypothesis. So your grammar is just distributed outside of this function. It exists in the list of syntactic operations you define here, and it depends on the processing of the final output, where you might want to check if the output is well formed, and many theories assume that there are further phonological processing here. Another part of this theory exists in our definition of the phrase structure objects, and also in how we define the lexicon and lexical items. But this function is written in such form that it doesn't really matter. And then I make another technical detail. And it's that here, when I'm creating the new syntactic working memory, I'm not making copies of the phrase structures in the syntactic working memory. So in fact, what I'm passing here are names that point to the same objects that what we started with. And this becomes a problem later if you have operations which change the properties of your phrase structures. So at some point you will have to add a function which creates copies from the phrase structure, so that each call of the derivational search function will work with its own copy of this syntactic working memory of phrase structures in that syntactic working memory. So that when you, at some branch of the recursion, you make changes to these objects, that you don't change the properties of for the other recursive branches. That would happen if you have only one set of phrase structures and you are just referring them from these different recursive branches. So you will have to copy the syntactic working memory each time you do the recursive call. But here it's not really needed, because we are just simply creating new objects and changing the contents of the syntactic working memory. We create that always anew, as you can see here, and we don't change any of the phrase structures that are given in the beginning or created in the earlier stages. So I don't need that here. So before I run and show what this script now does, let's just look how the script is, what the script itself is doing when I launch it. So this function, this definition here, and the phrase structure class, these are simply declarations or definitions that by themselves they don't do anything. They are just provided as definitions before we actually execute some actions. And here where all the action happens. So first we create, in this case we create 4 primitive phrase structure objects that will correspond to the lexical items, and they are simply artificially named A, B, C, D. They don't have any other content, and they are not supposed to be linguistically realistic. And if you want to run the script with, let's say, 10 elements, you can simply add them here by using the same formula. Then we create the numeration, and now for some reason I have added huge amount of, well, this was about some demonstration that I won't now go into. I was demonstrating the difference between set and list numeration. So let me just make the comment here. If you are using a Python list, if you use a Python set for the numeration as I'm doing here, then if you repeat an element, let's say as I just did, like right here, the A, then what happens is that there will only be one element A, because they are the same, and this is a set, so you're not allowed to repeat the same item. That's how the Python sets and all the sets works. If you want to create repetitions, you will have to create a separate object for your repeated constituent, or you can use a list. So if it's a list, then you can repeat. And then finally, we call the derivational search function by giving this numeration, the syntactic working memory, which contains the primitive elements first as input. And this will then bring us into this function which begins to derive the sentences. And here, the function which checks if the derivation is complete, it will simply check that if there is only one element in the syntactic working memory. This is the simple solution that we can begin with. And finally, the process, what it does with these final solutions, it will not do anything here. I'm just keeping things simple. What it does, it will take the remaining phrase structure from the syntactic working memory, and then it will print it. And this is because this would be now already part of the supervision layer. It allows us to see what kind of objects this function is actually producing. If you don't have this function, the script will run and it will do everything, but you just don't see any output. So that's why we want to print. We want to print the sentences that come out. And let me just quickly show what the print is doing. So printing in Python, can be implemented in this way, that we create this special function which has to have this exact name. And the Python then, when I'm sending something for the print function, in this case I'm sending the phrase structure object that was remaining in the working memory, syntactic working memory. The Python will then call this string or print function from that class. So in other words, printing a phrase structure representation will call this function because I have given it this special name. Why is this so useful? It's because you can create your own printing functions for all of your own classes and objects. So in this way I can tell the Python how I want to print out phrase structures. And what this function is doing is a simple recursive function which will use the standard bracket notation to illustrate the solution. So it doesn't really do any linearization. It doesn't produce sentences, because the point was simply to show the results, to show what type of complex structures this script is creating. But in a more realistic grammar, and when we have a data set that we want to compare our model against, this we would the post-syntactic function would use linearization. And in fact, in some of the later more complex scripts, I produce both the phrase structure analysis and then the linearized sentence. Notice that this is recursive algorithm, so we produce, if it's a primitive constituent, we simply print out its phonological exponent, the A, B, C, D in this case. If it's a complex constituent, we create a bracket and then we call the print function recursively for all the constituents separately. And then we just close the bracket. So this produces the hierarchical standard representation. This here, when we go through the constituents, is based on the fact that the phrase structure representations have a data item which contains the constituents. This could be a list or tuple, and I will return to this implementation later. I myself, in all my code, for just my own habit that I started very early on, used these capital letters X, Y, and Z, for example, to refer to phrase structures. This is not a good Python convention. If you follow the Python conventions, you would here have self. I won't go into this technical detail. I use self everywhere else except when I'm doing manipulations with phrase structures. Right. So let's put this aside now, and I will launch the command prompt, and we conclude by checking out what this script is doing. So here we are. And so we just launch the Python itself and give the name of the script as an argument. So the Python will then read that script and implement the commands in it. And that was the result. It produced a list of phrase structures that it created by going through all possible ways of merging items together. And this version prints only the final outcome, so we don't see the intermediate derivations. There are more advanced scripts which also writes them in a separate file. You can see that there are quite many. So this is a combinatorial function. If you go on and add, let's say, you can try, I give this as a homework, you can try to run this script by 10 elements and see what happens. But remember that because it's a set, if you use 10 elements, you will have to create separate objects for those. So don't repeat the same. It will not. The set works so that it will just remove all the literal replications, the same elements. Well, that was it.